All right, guys, it's 2 o'clock. We're going to get started. So welcome everyone to our virtual road trip webinar series. I'm Molly Soltis with Asphalt Testing Solutions and Engineering, and it's my pleasure to kick off our series with the evolution and use of additive session. We're joined by 4 industry experts who will discuss the where they are now of many well-known or well-remembered additives. And before I introduce them, let's go over a few housekeeping items. So the attendee controls appear at the bottom of your screen. In the bottom left-hand corner, you'll find the audio settings. You can adjust your speaker settings here. And since you're a webinar attendee, you're in listen-only mode. If you have an issue with sound, just exit the webinar and then rejoin. Moving to the right at the bottom of your screen, you will see the raise hand icon. Use this feature if you need something from the host. And if you have a question, please use the Q&A window. Open this window and type in your question, and we'll address questions at the end of the webinar. Now I'd like to introduce our panel for today's program. Tanya Nash has been a part of the asphalt industry for 18 years. She has a bachelor's and master's degree from the University of Florida in biomedical engineering. Tanya is the Pavement Materials Engineer for ATS and is a professional engineer licensed in Florida and Alabama. Phil Blankenship, owner of Blankenship Asphalt Tech and Testing, has been in the industry for 28 years. He earned his bachelor's and master's degrees in civil engineering from the University of Kentucky. He is a professional engineer licensed in Kentucky and Kansas. Dr. Gaylon Baumgardner has been a part of the asphalt industry for 35 years. He has a bachelor's of science in chemistry from Henderson State University and a PhD in civil engineering from Mississippi State University. Gaylon is the Senior Vice President of Ergon Asphalt and Emulsions and the Executive VP of Paragon Technical Services. Dr. John D'Angelo is the Chief Operating Officer of D'Angelo Consulting, LLC. He has earned his Bachelor of Science degree at Northeastern University and his PhD at the University of Calgary. He has been in the industry for 45 years, and he is a professional engineer licensed in Virginia and Florida. And with that, please make sure your luggage is stowed, your seatbelts are fastened, and tray tables and seat backs are in their upright position. Enjoy your trip.
All right, thank you, Molly.
Hey, Tanya, you're muted.
Perfect. Let me start again. So I'm going to try and give you a general overview of what we're going to talk about today with Gaylon and John. Overall, over the course of the history of asphalt and as the asphalt industry progresses, there have been many additives that have been introduced into the industry, make it better or to maybe kind of do it as a sustainability factor or a recycling issue. But it seems like that the market gets flooded with additives and we don't know what to do with them, or we don't know how to test them, or what happened to them after all of the hot topic items kind of dwindle away, or maybe a new secretary gets put in office, etc. So we just kind of want to revisit some of our old favorites, and we're going to look at a general category of modifiers. When we think of modifiers, the categories you end up looking at are like chemical, rejuvenators, or recycling agents, depending on what field you are of thought you're in. The recycled products, which is huge, a lot of polymers out there, and a lot of mix additives. You know, it could be everything from dry process ground tire rubber to fillers, fibers, etc. So the ones that you see in red that are outlined are some of the ones that we're going to try and hit on just up front to kind of get our conversation moving in the direction of what we think about when we think of the additives that were such a big conversation and everybody scrambles to try and address them, and then all of a sudden it's quiet, or it may be not a problem anymore, maybe not as big of a problem as people may have thought, or we found out how to use them. So we're going to go through and kind of just have a good conversation with John and Gaylon and see what their thoughts are on some of these topics. So kind of going off of that list, Gaylon and John, you can unmute. We also have Phil here with us that's going to help us run through some of these topics. And could you guys comment on something like, for instance, You know, one of the big topics, I remember scrambling when I was at the DOT and thinking about, oh my gosh, I would hear all these reports about re-refined engine oil bottoms. What are they going to do? How are we going to address them? And then all these task groups got formed. Can you comment about what happened in that category?
Okay, I'll kick it off. The actually, it's very interesting background behind that. That re-refined engine oil bottoms had actually been used very extensively for many years in the asphalt industry. It was primarily used as a sort of it's an additive, but just it was to make minor adjustments to the binders. Then there were a few issues that came about with some durability and cracking. There was some major concerns about maybe things like the engine oil bottoms were being overused. There was a lot of confusion about whether there were engine oil bottoms or polyphosphoric acid or several other materials that they leave similar traces in the asphalt, and that concern was sort of regional. And believe it or not, it was mostly the upper Northeast, the upper Midwest, were the two areas where they had the greatest concern. And at that time, a lot of highway agencies went in and banned the use of the material altogether. Other locations, never really saw some of the problems that were identified in the Northeast and the upper Midwest. So they really had not done much to address it and just let the spec stand as is. I'll let Gaylon wants to add to that.
I like to look at additives as how they affect the what I call the useful temperature interval of the binder. Before SuperPay, we didn't have a lot of things to really define that interval, but today with SuperPay, we can define the low temperature properties and the high temperature properties. And I classify the recycled engine oil bottoms in the class that Europeans would call a fluxant or a fluxing agent. And basically it's used to soften the binder without affecting the volatility. And that's the good thing about recycled engine oil bottoms is it does soften or help the low temperature properties without affecting the volatility like you would if you were putting a solvent or something like that in. The big issue with recycled engine oil bottoms is the amount that it took to change the material, say a grade, was excessive and showed issues with performance with things like delta TC. So typically the use levels were limited to about 5% because that would be an absolute maximum. So I would always consider them maybe more of an economic modifier than necessarily a property modifier, or more a tool that you could use for specific applications. I knew though that it has successfully been used though in some areas of the country as a blend stock for making asphalt that seems to have worked pretty well.
Now, can either of you comment on the effect possibly that you would see if you overdosed it by the mix? So the construction issues?
Well, it really wasn't so much construction issues with the recovered engine oil bottoms, except if it really overdosed it, then possibly you'd have a significantly softer binder. You might lose some of your high temperature properties. The real issue came about with the aging properties of the binder with time in the roadway, and that's really where we saw if you had put significantly too much, what you had was what they would call an unstable binder, or unbalanced, unstable, and you could have additional aging that would take place. And this is like if you tried to put 10% or 15% into the binder to really soften it to get 1 or 2 PG grades, where you think you'd have an extremely soft material that would have very good durability and cracking properties. with age, you'd find that you might lose those at an accelerated rate. And that was sort of the biggest problem with overdosing.
You know, John and Gaylon, like with all things, we got to be careful with moderation of these products. And what I'm wondering, maybe and Gaylon, I know from my days, and you and I've talked about this before. We used these as fluxing oils for years and years, but they were used very cautiously in industry. And it seems like when they became more commercially available at the contractor level or more mom and pops, people didn't mean to do anything wrong with it. It was economical, but all of a sudden we saw this maybe at a contractor level, 10 and 15%. Do you think that's where things went off rails?
That's possibly it, because really when you look at the residue for recycled engine oil bottoms, which is what we're talking about, it's really something that was actually taken out of the crude stream above asphalt, cut above asphalt, so to speak, or a lighter product than asphalt. One of the things that I've seen data and performance where it seems to act, because it's not really asphalt, so to speak, it seems to act, like John said, as an unbalanced or a two-phase type system where you've got the recycled engine oil bottoms dispersed in the asphalt. And so what I've seen is actually some selective absorptivity where some of the aggregates really have an affinity to the recycled engine oil bottoms. So what happens is that absorbs selectively the recycled engine oil bottoms. You tend to have a change in GMM, so your effective binder content goes down, and it leads to issues like cracking because you don't have sufficient binder for durability that you're looking for. So that's the thing. I just think that the overuse, that maybe people miss that, and then when you've got enough that the aggregate can absorb, then it takes all of the fluxing, if you will, out of the binder, so you don't have that really soft binder that you thought you had.
Thanks, Gaylon.
One product that I don't know if it's necessarily about a product that a lot of people were adding an excessive amount, but something that kind of came on the radar with the IMO 2020 was sulfur. Elemental sulfur, free sulfur. It depends on what part of this industry or what part of that process you are, of how much involvement you got in that conversation. But it did seem like it was kind of like the Y2K era. The Y2K came and went, and my gosh, everyone was unplugging their computers just in case. And then New Year's afternoon, you go plug it in and everything was okay. So is that IMO 2020 still a concern as far as the asphalts that we're going to be receiving, or what we're going to be sourcing? Is that going to cause issues down the road when it comes to looking at these new additives?
I actually think in the U.S. we're more prepared for IMO than they are offshore. I think that's what we have to watch for in the U.S. is watch for offshore materials that come in that may have issues with high sulfur content. I've actually had some discussions with some of the European suppliers, and that's been their biggest concern is they maybe haven't addressed it because they get materials from other areas that don't limit the sulfur content. So I think we've got parameters in place in the U.S. to try to resist the dumping of sulfur, if you will, into the asphalt. But we have to watch materials that are coming from offshore that are being imported as finished asphalt, because they will need to test those. But we've done a lot of things where we actually use sulfur to modify asphalt, and there are some issues with things like fumes, vapors, if you will, and also it seems to stiffen the binders considerably.
Yeah, the other thing too was that it was not so much that even again the adding of that sulfur to the asphalt, but for example, a lot of materials that were being used for things like bunker fuels and marine fuels, that if they couldn't necessarily easily be used anymore, could that then be used as it could be cracked and added to asphalt and really start to get products that were very much different than the typical asphalt binders we're used to seeing, and may have issues there too. But again, as Gaylon said, in the U.S., we don't really have a big issue with that yet, and but it has to be checked and followed closely.
Well, coming from a person, or maybe from the portion of the industry that is maybe 3 steps farther down from that point of sourcing the asphalt. Is there any concern that it's going to affect the properties in the long run? I mean, we're still adding the polymers, we're still making all these additives thing, and the compatibility factor, as we get as a purchaser of asphalt, we're not asking where it came from. We're not asking, what's the compatibility of this? What's going to happen to it if I have, am I going to have to put twice the amount of polymer in order to make it actually make a grade? Are we going to see some performance pushes on some of these asphalts that come from overseas rather than what we normally house closer to home?
Tanya, that's actually a good question. And Paragon is the technical support for Ergon Asphalt and Emulsions. And even though Ergon produces asphalt with their refinery, we're actually a net buyer of asphalt as a major supplier. So we have to screen a lot of different asphalts. And that's one of the things we've set up in the lab here, is to be able to identify one, performance properties, but also look at new things like Delta TC. And we're actually doing XRF to look at sulfur content and other metals in the asphalt, just so that we can know if there's anything strange with an asphalt, that we can track it down to know that it could be, if it causes any issues in binders or mixtures.
And then, it, like anything else, products change with time, always will. And, we're always trying to keep up with the testing to address, these characteristics. Because remember, these specifications are what we call performance related. They're not, performance, they're not direct measures of performance. And, when we find there's it was part of the, specification with MSCR, for example, we couldn't really identify the high temperature performance properties of polymers. So we worked on developing a new test. Same thing with durability and aging. We're looking at other ways to evaluate the binders, as far as Delta TC is one. It's not really part of the specifications yet, but it does a better job of identifying if there is the problem, say, with aging characteristics and cracking. We're still refining the best way to do that, what the specifications should be. So those are the kind of things that we're just going to continue to evolve with time. That's the only way we can catch some of these things.
Okay.
John and Gaylon, I'm going to throw a curveball at you. A lot of talk right now about rejuvenators, and I'm always, red flags go up when I hear that term, but I know we can use them right. And but you see a lot of people just putting in the bio oils, rejuvenators, fluxes, whatever it may be, and we put it in to soften RAP or RAS. We tend to treat RAP and RAS as just hard binders. What don't we know that we should know about cautions in using RAP and RAS and how all this works together, especially RAS?
Well, yeah, I think the biggest mistake we make with RAS right now is the fact that it is actually a modified asphalt in itself. It's not conventional asphalt like we use for paving. So it's not generally a paving asphalt, and we're blending it with paving asphalts. Basically, it's been highly air blown to, again, increase that useful temperature interval. While it's really stiff on the top end, sometimes the lower temperature properties aren't as good, and especially after it's been aged on the roof for, say, 15 to 20, 30 years. One thing that we've seen is maybe the issue is not necessarily the use of RAS, but maybe trying to use too much RAS. Because when you use 5% based on the mixture, that's 20% of the binder that you're replacing, and there's not 20% binder available in the RAS. I mean, it seems like it is because it's stiffening the binder considerably, but the effect on the binder is almost like I don't know exactly how to say it, is a pretty strong effect of what RAS does to binders, and it makes them age differently. So I think the key thing is to make sure we look at the performance of the recycled asphalt shingles and look at the properties to make sure we're not overusing, not using too much in a given mixture, and that'll help a lot. But also use softening agents. I hate to use the term rejuvenators, but use something that improves the RAS performance so that we get better aging in the overall binder, because it's that binder that actually performs in the mix. We just need to make sure we have sustained durability.
John, you know, when we were talking about this very thing, you said there's also a mixture issue with this too, that, you know, don't be surprised if you don't see all the asphalt coming off. Can you expand on that?
Yes, when you have an extremely aged binder, as Gaylon mentioned, you know, something that's on a roof now for, you know, 15, 20 years, maybe even 25 or 30 years, these materials are very, very stiff and extremely brittle. They don't melt necessarily at the standard plant mix temperatures. I mean, you know, this material stays brittle, and so it doesn't just, you know, it doesn't just melt and mix in. It has to actually what we call diffuse. And if you put two materials next to each other, even if they're not melted, they'll diffuse, where molecules from one will go into the other. But this takes a significant amount of time. I mean, even to the point where in some cases it can take years. And especially with the heavily aged RAS, you know, you put it in there, and it could take actual years before those materials diffuse. So in truth, that binder from the RAS might never really be part of the asphalt binder you're dealing with. You might just have some very, very stiff, very, very hard material, very, very brittle, that you're actually coating with asphalt, you know, new asphalt. And so therefore, you know, you've got a mix now that's extremely under asphalted. An important thing to remember, and I remember having arguments with some people about this, some of the very first use of things like RAS was not so much the use of tear-off shingles, but was the use of manufactured waste. Now, with a manufactured waste, this binder, even though it's heavily air-blown, it's not been aged on the roof for, you know, 15, 20 years, 25 years. So its properties, even though it is a highly oxidized material, it's not nearly as stiff and brittle as the tear-offs. Now, and so, you know, some work was done and got reasonable performance out of that, and people were happy. But when we started to go to the tear-offs, of course, now that's much more economical. People are trying to get rid of that, but you know, there you have a completely different animal.
John, I'd like to add to that just a little bit. Another thing, if you look at recycled asphalt shingles, you know, we already mentioned that the asphalt that's in there is an asphalt that's been air blown to modify it to give you a wide useful temperature interval. So it's giving you a very stiff asphalt on the high temperature end. But also the shingles are highly filled. Sometimes as much as 60 to 70% of a very fine mineral filler that can also act like a liquid, as we well know in some hot mix applications. So you're not just getting an extracted asphalt. There's also some granular material that was used as the surfacing of the shingles, you know, some glass fibers, what have you, but a lot of filler in there. So I like to look at maybe look at RAS as maybe more being a filler or an extending agent. And this is probably the most, the oldest method for modifying asphalt that we've had is using fillers and extending agents. So maybe the way to look at RAS is not look at it for binder contribution as much as what it does as far as extending the properties of the asphalt binder.
Well, that's very good. You know, and you know, putting all that together, John, I come from a mixed side, and Gaylon and I, chemistry was as a civil engineer was never my favorite subject, but I learned to appreciate chemists versus run from them. And you know, when I look, John, at this, you know, I think about, I may have a really good paper design, but then when it gets to the field, like a friend of mine always said, you can design it all day long, but if it doesn't construct as designed, you got a real issue. So just again, things that we need to be cautious and awareness.
Well, and that's a key part when we look at that. You know, especially some of the RAS mixes. You know, they're actually the workability is not very good, and you know, that's why they wanted to go significantly to warm mix to improve workability. And if that asphalt was really there, if it was really, you know, providing that benefit to the final mix, probably wouldn't have the significant problems that we see with, with workability. So I think that's the first indication that that you should tell you that maybe not all that asphalt is really acting as asphalt in the mix.
Well, it's funny. We always think of asphalt as a binder, but when it's elevated in heat, it's actually it's an oil. It's a lubricant. Yeah. Mm. Thank you, John.
So, gentlemen, kind of acting or continuing along the lines of that binder, what is and what isn't a binder. Asphalt itself is just a glue, right? It holds the rocks together that we have put in proportion. So thinking about some of the other alternative asphalts that are out there, like those bioasphalts, or I always called them the pigaphalts, the ones with the waste that was used in it, or the gilsonites. John, I've heard you speak about graphene before, and on top of some of the other smaller additives like the odor neutralizers in order to help compensate for some of these alternatives. Can you guys speak on some of these?
Again, Tanya, I kind of classify those you mentioned kind of like those fillers or extending agents, things that actually just improve the properties of the asphalt. For example, you mentioned gilsonite, gilsonite or Trinidad Lake asphalt, those kind of things. They're asphaltic in nature, or the way I used to like to put it when I worked for Seaplast, the Europeans call it bitumen. Well, while all bitumens are asphalt, not all bitumens. While all asphalts are bitumens, not all bitumens are asphalt. So you're blending bitumen, so to speak, because you could take coal and grind it, and you're blending bitumen with asphalt. So ground coal or carbon black or graphene, for example. A lot of different things can be used, but again, they're all like fillers or extending agents because they really don't have what we know as asphaltic properties, but they modify the asphaltic properties that we're using to produce mixtures and asphalt binders. And one more thing on the bio binders, or you call it the pig fault or whatever, some of the bio binders that are manufactured today for things like the colored asphalts, those are actually petroleum based in part because they start with something like a naphthenic oil that's modified with hydrocarbon resins to provide properties that are very similar. When I say properties, I'm talking about rheological properties that are very similar to like a 64-22 or the old AC30. And then they're actually designed to give us materials that give us either natural color or no color, or make colored pavements, because it's kind of hard to color black asphalt white. So that's where they come from. So they're a little bit different character as far as a synthetic binder, so to speak. And also you can use some of these vegetable-based materials, but typical what those are is naphthenic oils plus some hydrocarbon resins.
Okay. I think we're going to throw a little bit of a curveball at you guys and see. Let's talk about each one of you can go through one of your first modifiers that you've ever used since you've been in the industry.
John, yours will be the oldest.
So you first.
I don't know if I'd be the oldest, but no, when it comes to modifiers, I said I do remember working on some projects back in the late 80s when we were first introducing polymers into asphalt, and it was basically the probably an SB polymer, and this was in western South Dakota. Paving, this material had to be shipped overnight from Minneapolis and in the tanker trucks, and they were concerned about temperature and getting it into the plant on time, and keeping it hot enough, because most of the tanker trucks at the time weren't heated. So there was issues with the material cooling off and separation. They were that was a big problem back then too, because it's a lot of what we do now in the formulations. It was a lot more sophisticated than it was back early on in the paving industry anyways. So it was really sort of the start of that whole polymer modification of asphalts, and it's been growing ever since, though, because we found that even though it increases the cost, we get improved performance.
John, I always heard that date was around 1984. Would that sound about right?
Well, I think that was when some of the really first ones were used.
That's why I was saying the really early.
Yeah. My experience was probably about 88. Yeah, I was a couple of years later.
So I got it. Sorry, John. I know you're not older than dirt, but you remember when sand was invented, right?
Well, put it this way, I was actually, looking at paving projects back in the 70s, but I hadn't been really so much into the asphalt area at that point in time.
But that's important, because a lot of our vision, we tend to look at this and what we remember in the last 10 years, and it's important to know where we've been with all this. So Gaylon, Tanya's got it, over to you now.
I'm going to go back a little further than that, and it's not necessarily that I had experience back then, because I was a wee pup back then. But in the middle 1950s, two gentlemen won a Nobel Prize for polymer chemistry, Carl Ziegler and Giulio Natta, for what's called a Ziegler-Natta catalyst. Their work actually is what accelerated us into what we call this polymer age. I worked for a company, Seaplast Incorporated, which was owned at the time by L-Aquitaine, and they were one of the first companies to put SBS in a commercial asphalt product. It went into a roofing membrane back in 1966. At the same time, another company used waste polypropylene that came from this polypropylene production process that Ziegler and Natta catalysts produced. It was called atactic polypropylene, and it was a waste product, and there were just mountains of this waste product everywhere at the time, and they used that in asphalt in the beginning. So in the middle 60s, there were two primary materials. There was atactic polypropylene modified asphalt for roofing, and there was styrene butadiene styrene modified asphalt for roofing. So that was my first experience, was with those materials, and working for Seaplast in the late 70s, early 80s, was introduced to SBS modified, and actually the atactic polypropylene modified asphalts. And one reason we probably don't use them in paving is because, one, it's the high level of additive that you have to use to get this given properties compared to like SBS. And another is the fact that the processes have changed for producing plastics. For example, while they still use Ziegler-Natta catalyst, the most common method now are using metallocene type catalyst, which doesn't produce this waste byproduct. So there's not the waste material available anymore, which means those who modify with polypropylene have to buy a special chemistry to modify asphalt. So those are the ones that I'm the most familiar with. The one we see today in paving is SBS. Naturally, at loadings of 3%, is considerably lower, sometimes like 4 times, 5 times less than what you'd see in a roofing membrane, but it is the same polymer.
Okay. Can either of you comment on possibly a modifier or an additive that you think that does a good job, it does what it needs to do, but may possibly not get used isn't enough, or may get a bad name for some reason, or kind of in that realm of the idea of what's the best modifier that you've seen that doesn't really get used?
Well, I'll throw in on that one. I think, and it's there's a lot of reasons why it doesn't get used as extensively as it could, but I think, is the ground tire rubber can make an extremely good product. It ages well. You get good flexibility, extremely good rut resistance. But the primary problem is to get that, it's expensive. Usually the binder contents are a little bit higher in the mixtures. You have to use typically specialty mixtures, gap graded mixtures, to get the levels of rubber up high enough to really where you see the real benefits. I mean, we have some rubber modified binders that we use in dense graded mixes, but we find that they have a much smaller percentage of rubber, and you don't get quite that benefit. So, and they're also, very much, state of the, it's state of the art on how to produce them and place them, as opposed to the science. So, you need a significant amount of experience. So you just don't just sort of jump in and use them. It takes quite a bit of work of experience to get how to get them down properly. So it's got good points and bad points. I said, but cost is probably one of the biggies right there. Is it just to get the true benefits, you're going to have relatively high cost mix. So maybe in life cycle cost, it's beneficial, but in first cost, it can be very negative.
Tanya, before Gaylon goes, I have a follow-up question I want to hit on that here in just a moment, but Gaylon, go ahead.
I was going to, John kind of stole my thunder. I was going to say the thing about GTR. And I think one thing we need to do with GTR is, look at some of the processes that are being used. And when I say pyrolysis, I know that kind of drives people away from tire rubber because they think, oh, you're burning the tires. Well, you're not necessarily burning the tires, but if there's some way that we can achieve a point where we can get the useful part of the tire to put in asphalt and use the other parts that really just come along for the ride, like the fillers and things of that nature that can go back into tires or other production, that may be a more responsible way of recycling tires. And another thing, like John said, special mixes, looking at things like, hybrid binders where maybe we don't use, maybe part of the problem we have with rubber and why it's not used as much is what I call using too much and too big, where we use too large of a particle and too much and try to put it in a dense mix. And there's only so much room in a mix for these additives. So whereas maybe you use something less of a content of rubber, say maybe rather than 10, 12, 20%, you use like 5, 7, 8% combined with some SBS and, like a hybrid type binder, then you'd have more applicability in mixtures that are used more widely. I mean, the most used mix that we have across the continent is dense mix, not open graded and not SMA or gap graded mixes. So especially if we're going to try to improve our secondary roads, which a lot of those designs, because of cost, are designed either very close to the maximum density line or on the fine side of the maximum density line. And by doing that, it also limits what we can get in there. So if we can limit the quantity and the size, it may help us to use more rubber in dense graded mixes. Thereby, we would actually use more rubber overall because we're using rubber in more mixes.
That's a great point. Tanya, is it okay for me to do my follow-up here?
Absolutely.
So I look at these different modifiers that we have, and I think about all the things that we're measuring, but then I see new ones come into the market. And one of the complaints is, are we measuring the right things? I know NCAT's going to do a study, a big modifier study to try and understand our test telling us the right thing. So what tests are we lacking? Here's where I want to go with that, John and Gaylon. What tests are we lacking? What properties are we lacking, binder or mixture, that could help identify our modifier characteristics that we're just missing?
I frankly think we need to do more, and I know this is going to be probably not the best time. I just think we need to do more mix aging and test aged mixes to see how these materials perform with aging. I think we lack a little bit there. I think that would identify some of the lacking performance of some of these modifiers, or some of the things that we, it works great to modify binder properties to meet a purchase specification, but does it really perform that well in the mix? And I think by going to balanced mix design, that's going to help a lot, but I still think we need to be looking at how these materials perform with respect to aging. That goes back to what I said earlier about the recycled engine oil bottoms and selective absorption. Those kind of things you would pick up because you may not pick them up in just the general mix test, and you may not pick them up in the binder testing.
No, that's the key thing is, right now, for example, balanced mix design doesn't really look at age properties of these performance tests. They try to get a relationship to say, okay, if I test this material unaged, these are the results I get. And, and these materials it performs, basically this way. And so that relationship should be okay. But that doesn't really work when we start to look at new modifiers, because we don't know how they will affect aging. Not everything ages the same. And so it's going to be key to do that. And, we can then get relationships on a specific product later on to go into things like, quality control testing and that type of thing. But it's going to be key and to do that aging. But also, I mean, we have to look at some of the tests that we're trying to use, especially for balanced mix design. Those tests are great for, checks, for a basic mix design for certain properties, but they're not really, basic performance related tests. They're really very empirical, nature. And we do have, tests that, a lot more, mechanistic and performance related. And for the evaluations, we probably should go to some of these, things like the uniaxial fatigue test to really look at, how this material's going to perform, under repeated loading, different strain levels. And that's the nice part about some of those kind of tests is that we can change the strain in the test and look at it under several different conditions. We can change the aging. And so that gives us a lot more insight. Now, it's not something you would do for mix design. No, but if we want to do that initial evaluation, it's going to be key to look at those things.
Yeah, I've always found it interesting that we measure asphalt binder properties, but the one thing we never measure is how much it binds or how adhesive it is.
Yeah. I'm going to go back and add something too to the comment that John mentioned about or we mentioned about GTR. One of the things that's evolving today that was tried in the past that didn't work so well, and again, it goes back to that thing of maybe too much, too big, and that's the dry process rubber. And in that case, we have to test mix because extracting the binder from the asphalt is not the binder that we have in the mix, and it's not what we're looking at performance. So that's going to be highly dependent on balanced mix design. And I really think that without aging, you don't really incorporate the rubber the way it's getting incorporated on the road. So short-term and long-term aging would be a lot of value for using something like the dry added rubber, because I know it's being used more and more by different agencies. And I know they're using finer rubber and additives to help get it more dispersed and get the performance that we didn't see from the materials of the past. So if we're going to get products like that accepted and they're going to get good performance, we have to make sure, one, we design right. One thing that I see with that is, like John mentioned earlier about the binder content, because of the way we add the rubber to the mix, we're actually putting a little more binder in those mixtures than we are with, say, a terminal blend rubber modified asphalt, because the binder content is designed for that those volumetrics, and so it's typically going to have a higher binder content and you get better performance.
Well, guys, we do have a couple of questions posted here. I think I'm going to just start trying to go through a couple of them for you. We have a question that says, as a modifier with latex and GTR, I've seen sudden changes that shows a weaker product and suddenly need to increase the latex by 50%. I always suspect rehab. Any thoughts on that?
I wonder what kind of region they're talking about. Like, is it a region where they have really soft binders, or typical binders like in our region of 64 minus 22? When you look at SBR, it is a little more difficult to modify with SBR because it's a film forming polymer, and it's a latex also, or a dispersed polymer. So it's harder to get in the asphalt. Typically they inject it at the plant. There are suppliers that used to actually flash off the water, in storage facilities and actually have a modified material. But with the advent of SuperPave, it became a little more difficult because the materials tend to like to gel, if you will, the SBR. So when you're in a tank, it just makes it difficult. One, it makes it difficult to test, especially when you do the RTFO test. It tends to crawl out of the bottle and what have you. So it is a networking film forming polymer that acts differently. So the reason I asked the question about where it is, if you're trying to start with a very soft binder because you're trying to meet low temperature requirements, sometimes that may be part of the issue, because another thing about SBR is it's not very soluble in any solvent. In fact, it's not totally soluble in any solvent known to man. So asphalt's not a very good solvent, so it could be swelling the polymer and causing issues that make it change the properties also. So it could be the cure time, if you will, of that polymer in that particular asphalt. The asphalt's really soft, got a lot of solvent in it. It may be causing the polymer to swell to give properties, and then just vice versa. If it's a harder asphalt with not a lot of solvent, it may not cause the polymer to swell and give you the properties you're looking for.
Okay.
Which it sounds like that's what that is. By having to add 50% more, it's probably more because of the solubility of the polymer in the asphalt.
Yeah, and then I'll just throw in, the question was it, rehab? Well, it could be, but it
Yep.
could be any of a lot of other, you know, oils and that get added to asphalts to get a base property. And so, you know, they all are going to affect how that formulation works. And, you know, what works great with one base asphalt, when you find, you know, something slightly different, it, you know, that just formulates very differently. Then we see that, you know, not with just things like GTR and SBR, but even with SBS, you know, how that material is going to go in changes based on the crude source of the asphalt you're dealing with, and how that asphalt was actually formulated. Because even asphalts like a 6422, that's not just something that, you know, it's probably one of the most basic asphalts, and it is probably one that's usually not too much manipulated to get the grade, but sometimes they do. You know, if you have a base asphalt that gives you a 6416 and you want to make a 6422, you're going to have to get some other soft oil from somewhere to soften that up. And so it's going to change the reactions.
Another thing to look at, you know, just as a general comment here, you know, think about these materials we've talked about, SBR, SBS, ground tire rubber. They're very similar polymers, all three of them, you know, as far as the nature of the polymers. They're styrene butadiene type polymers. One of the key things is the fact that they're really not blends. Those polymers do not melt in the asphalt. They're dispersions of those polymers in the asphalt. And the more finely you disperse that polymer and allow it to interact with the asphalt, the better the performance you're going to have. So in something like an injection of an SBR, unless you have really good mixing, you may be having very large, if you will, particles of being dispersed in the asphalt that are acting very much like independent phases. Whereas if you have some type of a high shear mixer in line at the same time that helps disperse that material, it's going to give you better performance. And that's the same with a lot of these additives, because they're not necessarily, they don't necessarily melt. I can think of one that was used out west back that was actually a chemical additive that had a melting point of 900 degrees. And the person who was using this said, well, it works better when I use the aqueous form of that rather than the solid form. Well, it's not melting in the asphalt. Asphalt, we don't get to those temperatures, and unless you grind it and disperse it well, you're not going to get the same performance of that aqueous material that you're dispersing better, because you can disperse it more finely. So it's kind of like an asphalt emulsion. The more finely you disperse the polymer, and the more uniform, the more stable the material is going to be.
Well, thank you guys. There's another question kind of going along the GTR pathway. It says, I agree with John's suggestion about GTR's mixed performance. I wonder if we may have the same results with conventional PMA if we use the same high binder content as the GTR mixes.
Well, let me say, I think we can probably use higher binder contents with the polymer modified mixes than we are using, because you know, I think that we really addressed a lot of the rutting issues with you know, the aggregate structures and the stiffer binders, you know. And you know, I know there's a big concern that, you know, you don't want to go back to the rutting issue, but the truth is, one of the best ways to take care of cracking is just to put a little bit extra binder in. Not a lot, but just a little bit extra. You can dramatically improve the cracking resistance by improving that. And you know, I really always felt, and you know, that was part of the reason I really pushed the MSCR, is because I think we were putting too much polymers or not putting enough asphalt in the mixtures, you know, to get the rut resistant part. We don't really need all that. It's there. We get good cracking properties. So maybe if we do go with just, you know, an increase in the binder contents, you know, we'll have dramatically improvements in cracking. Again, of course, now when you do that, costs go up, and no one wants to increase costs. But you know, if it's life cycle cost, and if people start to really take a hard look at life cycle cost, then you find out that you actually might be saving a lot more than you're spending.
John, you made a good point there about the polymers and the binder content. You know, if we go back and look, I think it was maybe the first cycle of the NCAT test track, there were some sections where they did increase the the binder content in the mixes. And I think that was mainly focused on rutting back then. That was early, I can't remember the years, but it shows how old I'm getting.
But
Anyway,
2000
it does get
2000.
yeah,
It's about 2000
anyway.
Gaylon.
So you look at the early test tracks, and we were looking at rutting. Well, some of those sections, I recall that they actually added, I think it was either 0.5% more binder in compared to the ones that had the normal binder. And I think we did see better performance, but the issue was we were looking at rutting and not cracking. Maybe we should go back and look at very similar mixes that we've got that kind of rutting performance on and see if we can see the improvement in durability with some of the newer tests that we've developed.
Yeah, that's a good point, Gaylon. We have one I think it's a comment. It just says dry mix GTR. And I think that was just a plug to say, let's use dry mix GTR.
Yeah, I see who is making the comment. Yes, and I mean, dry mix. If it's done properly, like anything else, you can't just throw it in. All right, it's got to be engineered and put in properly. It can work extremely well, but you have to take into account the issues that the rubber is going to absorb asphalt, or portions of the asphalt. So you in your mix design, you have to account for that, and there's different ways of doing that, and I'm not going to get to it here, but you have to account for that. You have to make sure that the size of the material you're putting in is compatible with the mix, as Gaylon mentioned earlier. You don't want to throw big chunks in a dense graded mix, because what that's going to have a tendency to do is push the aggregate apart, and maybe you'll lose some of your aggregate structure. So but it's when you put all these things together properly, you can make a really high quality mix.
And some of the new materials compared to the older materials are just what John says. I think I can mention this because it's not sold anymore. For example, if we go back to the old Plus Ride, I think the biggest issue there was the size of the rubber. I don't think it was a bad concept. I think it was the size of the rubber, because rubber that's used in other countries where they use finer materials, even some of the 80 mesh material from Rouse that was used back at that same time, that seemed to work really well in Florida. That was before your time, Tanya. But anyway, it seemed to work pretty well in Florida as a dry addition. So some of the newer materials with finer rubber, and like John said, well designed and well formulated, could probably give performance looking more. That's why I mentioned what I did about, we need to look at aged mixes and look at how it performs with aging to make sure that it's getting incorporated the way that we think it is. Can't do an extraction and test the binder, because that's not the real world.
That brings up an important point, Gail. We see a lot of modification now, whether it's warm mix additives or whatever it may be. We seem to be moving some things back to the hot mix plant where we had moved it upstream to the terminal. So I guess my word of caution to contractors is it's sort of a buyer beware. As you see all these things coming your way, a couple of takeaways I'm hearing is make sure that you're aging things properly. Make sure that they don't work just for construction, but they work over a long term, that they're working in your volumetrics, but also, we're going to put a lot of faith in some of these tests, such as Ideal CT and SCB, and I think they're good tests. But one thing they don't do is they don't have a relaxation phase. And like what we would with fatigue or things like that, or, some of those other fundamental tests. So I think it's one of those that just because the test tells us it may be the best thing since sliced bread, or it may not work at all, just keep your eyes wide open and realize that maybe these tests can't pick up on some of these newer things that we're finding. Fair to say?
Yeah, I believe that's super fair. Yeah.
That's
Sorry,
key,
John.
Phil. No. But yeah, I mean that again. That's if you just have one loading rate, and one failure, if you can't test it at different conditions, at different temperatures, different strain rates, different frequencies, that's when you start to really understand, the real performance characteristics. Now, then you can switch back to the simpler tests once you've identified all the issues that are there. But it's key to do that.
Going along the same lines of the aging aspect, the use of the weatherometer, is that a good method to address, maybe simulate the mix aging for the additive and product evaluation for balanced mix design?
John, so I don't act like Horshack here. Anyway, my thing about the weatherometer is, you know, I understand for surface aging and everything, and I think it could be useful. The biggest issue is how do our pavements age at depth? You know, we know from Coons and Wright that most of the aging happens in that top half inch of the pavement, you know, initially, and that's where we need to address it. Well, the aggregate there, for example, if the weatherometer is a UV weatherometer, the aggregate is pretty much preventing penetration of the UV light into the surface. So most of that aging is thermal. I think that it is important to look and see what the effects of the UV light is, but I don't think that should be your only method of aging. In fact, I know there was some work done by a student at the University of Texas that actually looked at the penetration of UV light into the surface of hot mix, and it really wasn't a big contributing factor of the aging. I do feel like, though, we need to have some way of aging. If we're going to age, for example, cores in the lab, a way that we can age those to simulate the substrate or the base as a heat sink and keep the temperatures constant on the lower portions of that core, so that we're only giving the surface, that half inch that ages, give it the aging that we're looking for. And there's some things that are being worked on, me in particular, to look and see if we can kind of simulate that in some type of artificial weatherometer. But I really don't think just UV is the best way to do it. I think it needs to be a combination of maybe UV and infrared or thermal heat, because probably along with oxygen, thermal is probably the second, or probably the primary aging factor.
Just to add to what Gaylon's saying there, you know, it's nice, and I think it's probably more an issue with things like top-down cracking, because, you know, there we're talking about the high shear stresses right at the edge of the radial tire, you know, initiating that crack and then watching it progress downward. Once you get that initiation, then you get a weak spot, and it continues to grow, and so yeah, maybe something like a weatherometer can help with that specific issue. Whereas some of the other agings that are much more accelerated, and I like them and I use them, things like loose mix aging, but that gives you a general overall aged mix. Then you can make a specimen, and when you do some of the more, you know, mechanistic based tests, you can sort of try to figure out how those materials are going to, but they're not going to simulate what's really going on in the real world in the field. So yeah, a combination of, you know, as Gaylon said, maybe some UV and moisture, but also doing a better job of controlling the temperature in that specimen and how it changes would address a lot of the issues with things for like top-down cracking and block cracking, that type of thing. But again, it's a very specialized area. But I guess top-down cracking is, I think, at this point in time, becoming much more of an issue than some of the other types of cracking we have. I think, you know, we know fatigue is really related to structure, and you make it a little bit thicker and you eliminate the fatigue. But, you know, top-down cracking, you know, you can have, you know, a pavement 24 inches thick, but you can still get that cracking starting and then have it start to progress downward.
And John, it's, you know, it's interesting with the top-down issue we're having, and now these pavements are all out there. This is not something we fix overnight. You know, this is it's a long-term issue that we got to go back and fix, and lack of funding in some areas. And John, you're up in DC. Help us get that transportation bill. You know.
Yeah, I'll go with my picket sign in front of Congress and say, vote on the bill. Vote on the bill.
Well, gentlemen, kind of is a good transition. We have let's get one last question in, just to address that top-down cracking that you brought up. And the question was, I believe our industry has fully recognized the benefits of PMA in improving the rutting and bottom-up fatigue cracking performance of asphalt pavements. But what about top-down cracking? Should we expect to see the same performance benefits on top-down cracking performance?
I think go ahead,
yeah.
John.
I'm sorry, Gaylon. No, how you get?
I was going to say, I think this discussion we just had, I was, as what's funny, as we were having that discussion about the weatherometer and things like that, and John mentioned top-down cracking, I was thinking the same thing, is maybe that's the way we look at it. If we start trying to focus on that top half inch and try to simulate what we see in the field. And I said, go back to Coons and Wright and look at what they talked about with aging. And I know Jerry Reinke's done a lot of work with torsion bars on mixtures and things like that to see if we can simulate the aging in the top, especially in areas where we have top-down cracking. And if we can simulate the aging, then maybe we can come up with a test or some way to predict it and see if there's any improvement in performance against top-down cracking.
But yeah, and but I think the polymers, you know, they do improve flexibility, and you know, and retard the whole issue with top-down cracking. And we even see in other cases where agencies put down these thin microsurfacings to slow down aging of that surface, but it's also the highly polymer modified, very thin layers, so they can handle the shear stress of the tire and at the same time not rut because they're very thin, very angular aggregates, highly polymer modified, a lot of binders, so that you get the benefit of everything. You get high binders and high polymers for flexibility, thin layer to start and seal to prevent aging for the lower layers. So, you know, those are kind of things that, you know, can really address some of the problems we're having. They're expensive, but again, they're so thin sometimes, you know, the overall cost. But a lot of agencies hate the idea of having to place something like that, you know, within a year. I said, I just put a new pavement down and I got to put an overlay on it within a year. Well, yeah, because that's when you need it. You got to stop that aging before it happens. If you wait till it's 10 years later, it's already too late.
Hey, John, you really just gave me an idea. If we want to simulate top-down cracking in the lab, just paint a thermoplastic stripe across the top of the core and it'll start to crack on the side of that strip like it does on the pavement.
Well, yeah, we see it all the time. We see it all the time on paint stripes.
That's
you
what I
look at
meant.
the white paint. You go see the white paint stripe on the roadway. Where's that crack? Right around that white paint stripe.
Okay, thank you guys so much for spending a couple, well, I guess about 62 minutes with us this afternoon. It was a great conversation, and thank you for all of you remotely who joined us today. A recording of this webinar will be made available, so watch for that. And we hope you join us next Thursday, October 8th, for our next trip in the series. Have a great afternoon, everyone. Thank you.
Thank you, Tanya. Thank you, Molly.
Thanks, everybody. Thanks, everybody.
Thank you, gentlemen.
John.
Thank you. Bye-bye.
Bye.